today's lecture is Computer Vision 101. We're going to learn the absolute basics of the structure of the field of computer vision in the next hour or so. And when we think about computer vision, the first question that comes to mind is, what is computer vision? So does anyone have a definition of what computer vision is?
So I would tell something that if my machine needs to look at its surroundings, my machine needs eyes, it needs to focus on something called computer vision. It gives eyes to your machine and your machine can know what your surrounding is.
Excellent.
Adding to what Shikhar said, I think it gives a machine the power to understand from the images. I mean, just watching something doesn't really help unless it gives you the information from digital data, digital images.
It's a part of artificial intelligence that trains computers to interpret and understand the visual world.
Okay, all of these are excellent definitions. All of them are correct. And I'll just give you mine. Teaching machines how to see. Very similar, almost the same as what many of you have given. I like the second to last answer about how another interpretation of computer vision is you have AI. AI is artificial intelligence, which means effectively you can define it again in many ways, but effectively creating some sort of human-like intelligence in machines. And if you look at AI, it's very often divided into two sub-branches, which is how do we understand images, which is vision, and the other one is language. How do we understand speech or written text? Okay. And so these are just three kind of subdivisions of AI. So the two divisions of AI. So in this framework, if you look at a modern department in computer science, very often you can think of specializing here as kind of a general AI scientist, or you can take one of the subspecialties here in vision and NLP. And you see this with your industry, right? Of course, NLP, we see it very often with communication, smartphones, and so on, smartphone assistants, and the list goes on. Vision, which is the topic of today's lecture, has many subparts and applications, like the autonomous car, smartphone camera, medical devices, and much more. Okay? All right, so now with that preamble, why should you study vision? Well, this is a slide that I also use at UCLA for some of the students. And money is not necessarily a reason to study a field, but the interest from companies allows you to build technologies that can reach a lot of people. Companies are a channel that enables you to reach a lot of people and impact the world. Money is simply a byproduct of that. Okay. So the sponsors of the academic conferences in Vision are often the hot employers that we kind of think about when we talk about cool companies to potentially work for. So vision, if you think about it, is this idea of taking an image, which is an array of numbers. So on the left-hand side, you get a matrix of numbers, and you want to infer meaning from it. The image on the right here, this kind of graph on the right, is how a mathematician might look at an image. It looks like kind of like a, some sort of height map here, right? Here's your X and your Y pixel, and then the height is the pixel intensity from 0 to 255, which means that it's an 8-bit image here. And so if you look at this type of a data structure or image, you can see that it, depending on how you represent it, it doesn't look like our kind of everyday image. This is a simple image of kind of an office scene, but it doesn't really look that way. So images are complex. So think about it from this lens. Let me ask a few quick questions here. How many different 8-bit grayscale images of size 640 by 480 can you count? So how many different images of 8 bits at this kind of VGA resolution exist? Okay, so we have an answer in the chat, 640 by 480 by 2 to the 8. Okay, cool. So how much does that give us? All right. Now, here's a follow-up question. How many particles are there in a universe? Yeah, something like, 2 to the 80. Roughly, I'm just going to round it off as 2 to the 100. Okay. That's how many particles are kind of estimated as being in the universe by some measure. At least particles that we know of, right? There could be, different types of subparticle particles, but there's about 2 to the 100 things in our universe. How many images has humanity seen?
Finite set.
It's a finite set, but you can count it, right?
Yes.
Imagine we see about 10 unique images per second. We live about 100 years, and humans have been around, for about quite a lot of time. So let's roughly approximate it to 6 million years for how long humans have and will be around, if not more, hopefully. So you've got 6 million times 100 years. You have to convert 100 years to seconds, right? So does anyone want to complete it here and give it to me in terms of an exponent, like 2 to the what? Yeah, it's a very, very large number. Okay. So the number of possible images that kind of exist is very, very massive. So it's a very strong form of unstructured data. Now, why should we study vision? So this is a kind of map of a part of your brain. You can see these V1 neurons and other neurons and tissues in your brain structure. And if you look at this brain map, about you can kind of see it up here, about a good, quite a good fat chunk of your brain is shaded in here because it deals with visual processing. There's a saying that again, it's kind of approximate because neuroscientists are still discovering the brain, but at least in computer science, we can take what they know for faith. Based on current knowledge, it's estimated that about 70% of the brain is processing kind of visual information. So 70% of our brain is devoted towards processing vision because it's so complex, as we saw in the last slide. For this reason, solving the computer vision problem is often seen as the gateway to AI. This is, does anyone recognize this image and who's in this image? Yeah, Hubel and Weasel. Does anyone know what they're famous for? I don't know if this is gonna help. This is a diagram of their experimental setup, seen in a very low resolution camera. Yeah, there was an experiment with an animal, and Hubel and Weasel were kind of neuroscientists at Harvard University in the 70s, about 50 years ago. And basically what they were trying to do is they were trying to see, okay, how does the brain process visual information? So what they, to rough approximation, what they did was they connected electrodes to neurons in an animal and showed the animal visual stimulus. They showed them all types of images, like famous paintings, Mona Lisa. Maybe the animal would be shown its counterpart in a different gender, for example. So the animal was shown images that were thought to maybe evoke some sort of emotion in the animal, but the neuron would not respond. So Hubert and Wiesel were at the point of their careers where they were trying to get tenure at Harvard, and so they need to make something work, right? Otherwise, you don't get tenure as a professor. And so what they did was, essentially they had a research assistant, and they were getting very stressed, and they just created this whole. They showed this cat almost every type of image that they could get their hands on, but still they would get no response. So at this point, they thought, okay, well, somehow the neurons that connect to the eye are not being strongly activated, right? Somehow, for some reason, these neurons are not being activated in some sort of predictable pattern. So maybe there's something that we just don't know about how the brain processes information. And this experiment has been largely a failure. So as they were packing up the experiment, the laboratory staff, including themselves, on the last day, they forget to clean up the experiment, okay, properly. So what happens is they leave, there's a glass slide here on which at the time, remember this was before we had screens that like displays that we have now. So the way you would project an image is you would use what's called a slide projector. I don't know, does anyone remember slide projectors? I think I'm probably dating myself, but when I was a kid in school, the school courses were done on slide projector, okay? So they had a slide projector, and what they did was you have a slide on the projector, and they didn't align the slide properly on this last day. So here's your slide projector. Okay. Here's your overhead projector. This is your lamp. Okay. And it's kind of projecting here. And then you can kind of see a bigger version of this. Now, what they did was the slide was not aligned. It was placed like this. So if you think about it being placed like this, the slide projector was projecting an image to the cat that looks something like this. And so now this type of image immediately started a recording of electricity at that neuron. And so they were confused. They said, well, this isn't really a cool image in any way. So they took it off and said, okay, maybe I have noise in my experiment. They repeated it, same thing happened. Then they tried placing it this way. A different neuron was activated. Then they tried changing the stripe pattern. Yet another neuron was activated. So the idea here was that the visual cortex, at some level, the neurons that are immediately connected to our eyes are processing information, basic information. They respond to basic information like blacks and whites, like the difference between black and white. Frequencies, effectively, stripes, right? They're responding to stripes. And it's this process as it starts to cascade into the brain that eventually gives us higher level meaning. And that was the outcome of this experiment. It turns out that this kind of paradigm of how vision is processed, whether it's biological or whether it is artificial, it's effectively a very similar idea, which is that you take an image, a complex unstructured picture of which there are as many atoms in the universe, and you break it down into stripes, and then you break it down into collections of stripes. And eventually, as you keep breaking it down, you're going to end up with different scales of feature processing. And so that's what our brain is doing. And that's to an extent what neural networks are doing today. Okay. So there's some very exciting areas in neuroscience, and I don't know if any of you recognize this picture of how the brain can adapt. There's the changes in vision. This is a man named Phineas Gage back in the day. A railroad spike went into his brain, but actually he was able to recover because the brain had a level of plasticity where other neurons started to compensate. Now, moving away from neuroscience briefly, let's return to the question of why vision is difficult. Here we have a couple scenes. On the left is we have kind of a landfill or a garbage dump. And imagine trying to find a specific piece of garbage. Maybe you're doing a recycling. There's a lot of companies, for example, that are doing automated recycling from images. So there's a lot of clutter there. On the right-hand side, you also have quite a bit of clutter. This is, for example, microchips. You could be trying to find defects in the microchip, or many times people are looking at taking a picture of a circuit board and re-engineering the circuit. This is done by some governments that are kind of trying to protect trade secrets of how electronics work, right? Because electronics ultimately power all the data that we have. So there's a lot of computer vision work looking at how do you take a picture of a circuit board, like the one on the right, and how do you infer, use an AI to infer the processes of the circuit. So that way, if you get a circuit shipped from, I don't know, some other country, or let's use an alien planet, like an alien gives you a circuit, how can you be sure that the alien has not put a listening device in that circuit? And so that's kind of studied actually as a computer vision problem. So on the right, we have, does anyone recognize the gentleman on the right? Does anybody want to offer his name on the right? Shannon, right? Claude Shannon, Shannon's sampling theorem. So what happened in the 50s and 60s and even 70s in the electrical engineering world was that people started to understand how to represent information. And it ties into what was said in the beginning of the class when a student offered the definition that images are information and computer vision is trying to extract that information. So one of the key questions that we look at is something called representation. So what is the function of the data that we should store in memory so it'll be useful? That's one kind of area of vision. What is useful? Like, what does it mean to be useful? What is information? How do we measure useful? And so on. So you have all these principles of what is optimal. And if you decide to become a practicing, I would even say engineer, you don't need to become a scientist in this regime. This is all engineering. You have to think about these engineering questions, or if you prefer, scientific questions. Just as an example, some of you who have more of a kind of a background in vision, you might think some of these ideas are trivial, right? You might say the best representation of data is data itself. Anyone familiar here with the data processing inequality?
Yeah, it says that if we have a Markov chain, x to y, y to z,
Yep.
then the information about x in z, there is it compares the informations between xz and yz.
Mhm. That's right. So in some ways that solves the representation problem of computer vision, right?
Yes.
Who's here is familiar with inductive bias? Kind of raise your hand if you understand most of these terms.
So
Okay.
is inductive bias the learner bias?
Yeah, think of it like the learner bias if the learning process is inductive. Yeah.
Okay, so like we make a few set of assumptions before we train something, and those assumptions act like weights, which we indirectly call them as induction bias.
Yep. Exactly. Okay, so we'll kind of double click on the more advanced stuff in a moment. So those of you who are familiar with these terms, it might seem like these questions are easy to answer because you can just apply these mathematical ideas to it. But let's go back to the 60s again. Look at the date here, July 7th, 1966. Before we were, I guess, all born. So this was a project at MIT called the Summer Vision Project. And effectively, the Summer Vision Project was an attempt to use a couple undergraduates from MIT to do some kind of work on, you know, interfacing a camera to a computer and having the computer tell kind of what it sees. And unfortunately, this proved to be quite difficult. I mean, we're still working on this topic, right? Of having a camera tell a computer what it sees. So the Summer Vision project did not really pan out in that summer. It took 70 years before we were actually able to really tackle these problems well, or maybe 50 years. But vision is that seemingly kind of simple process that is actually much more complicated. All right, so if we continue, what is intelligence? Well, in this kind of course, intelligence has many forms. We're going to think about intelligence being defined in terms of the vision process. So if we can solve vision, then we can essentially create these intelligent machines. So those of you who are interested, you can read the McCarthy book on intelligence. All right, so we started with some biology, some biological motivation. We talked about how vision and intelligence are linked. We talked about a little bit of mathematics that can be applied to thinking about vision from information. There's another way to think about vision, which is that vision fundamentally starts from light, okay? So what happens is that when you have a scene, you have light shining on a surface. This light hits a surface and then bounces off, right? And so fundamentally, if you think about the Hubert and Weasel experiment, ultimately at the end of the day, the eye is just nothing but a light measuring sensor. You have these special kind of cell structures in your brain, in your eye, that respond, that fire a neuron when light hits. Okay. So ultimately, light is that initial stimulus. Therefore, maybe vision should be studied from a physics perspective of light. Okay. So imagine here we have a scene and we have a sun or a light shining on the scene. The problem with studying it from a physics perspective is that the real world is very complicated in terms of its physics. when you send a beam of light, it starts to bounce off into many other beams of light that all go and smear together and kind of create this mess of reflections in your eye. So somehow your eye needs to be intelligent enough to go and tease out these beams. And obviously it's not solving a physics problem, right? Where you're actually decoupling the multipath. It's doing it with the kind of a reasoning approach. It's much like the analogy I would give for why you can't always think about vision in terms of the physics is think about a child trying to catch a ball. Like imagine that there's I don't know, a baseball or a cricket ball that is kind of been hit, and it's in the air and it's kind of has this trajectory. Now there's two ways to look at that. You can probably like go and do all these calculations on the blackboard and figure out where the ball is going to land, or a child could just see it and then catch it, right, where it's going to land. How is a child able to do that? Well, even a children's brain is able to go and reason about complex physics through some other mechanism. Okay. So one of the things that areas in vision is how to link the physics of the process here to reasoning, trying to kind of look at, all right, if the child is looking at this ball, the ball has these equations, the child doesn't have these equations, how do we reconcile these two models? And that's kind of an area of physics-based vision. To give you a sense of topics that are studied in this area, think about the difference between measuring light versus measuring scene properties. So here, if you just think of it as a light measuring idea, then you're going to measure a square and then kind of like a couple odd shapes, right? Like a J shape here. Okay, but we know that blue thing is not a J shape, right? Most likely. Most likely, if we were to see something like this in the world, it would be a square. The green thing, that could be a J shape because we see that kind of spacing between the red square and the green. So measuring light is important. It's a necessary condition. You need to measure the light, but it's not sufficient for reasoning about the scene. Okay. So vision, it is important to measure stuff, but it's not always what you measure. So for example, here is a slide from Ed Adelson, one of our colleagues here. And what you have is you have a scene. And let's look at two of the squares. Let's pick square A and B. Probably you can guess what I'm going to ask, but what's the brightness? Which one of the squares is brighter, A or B? So we have a variety of answers. And actually, if I take the same image and I remove everything else, you see that A and B are the same brightness. Now, to be fair, this depends on your brain to a degree. Each of us has a slightly different brain that does different things. So we don't see it all the same way. So many of you, I'll recap how my brain kind of sees this, which is that in this particular image, A looks darker than B. Okay. And the reason is because even though the brightness, the number of photons that my eye is measuring is the exact same from A and B, right? Because they're actually the same color. This pixel on the display is emitting the same light as this pixel on a display. Your brain artificially boosts this brightness because it says, well, this square is supposed to be in a shadow. So its real brightness, quote unquote real, should have been greater. So vision is not always what you measure, and this causes sometimes, this causes kind of a perception gap between what machines can perceive and what the human brain can perceive, right? A machine, if you were to take this image and digitize it, it would simply see that A and B are the same color. And so this is kind of a failure case of neural networks today when it deals with information like this. Here's another one, which I'm not going to get into in the interest of time. This is called the Ames room illusion. If you like, you can, I'll give you kind of a problem on the break you can chew on. Is if you think about the Ames room illusion, you have these three people with different heights. It turns out that these people are all the same height. Okay. In this picture, the people you see here are all the same height. So what's going on? Think about it in the break. So another problem that makes vision very hard is that objects have kind of varying appearance. And I believe this slide also has recursive credit.
Hey, Achuta, the audio, are you speaking?
No, I'm not speaking right now. So just
Okay.
so this slide has recursive credit to Svetlana Lazenby at UIUC. So in this slide, you have the same object, which is this chair. It's the same object class. So maybe you want to draw a bounding box and call this a chair. But the problem is, technically, this is also a chair, and so is this, right? So there's a certain diversity here of objects in the scene, and your goal should be to make these algorithms that you generate invariant to these diversities. Okay. What I'm going to do now is I'm going to show you a quick video. So I'm going to stop sharing my screen.
We can.
Yeah. I think almost every automaker has some electric vehicle program. They vary in seriousness. Some are very serious about transitioning entirely to electric, and some are just dabbling in it. And some amazingly are still pursuing fuel cells, but I think that won't last much longer.
But isn't there a sense though, Elon, where you could now just declare victory and say, you know, we did it. Let the world electrify, and you go on and focus on other stuff?
Yeah. I intend to stay with Tesla as far into the future as I can imagine. There are a lot of exciting things that we have coming. We've got obviously the Model 3 that's coming soon. We'll be unveiling the Tesla semi-truck. And
okay, well, we're going to come to this. So Model 3. So it's supposed to be coming in July-ish.
Yeah, it's looking quite good for starting production in July. Yeah.
Wow. One of the things that people are so excited about is the fact that it's got autopilot. And you put out this video a while back showing what that technology looked like or would look like.
Yeah.
There's obviously autopilot in Model S right now.
Yeah.
What are we seeing here?
Yeah, so this is using only cameras and a GPS. So there's no LiDAR or radar being used here. This is just using passive optical, which is essentially what a person uses. The whole road system is meant to be navigated with passive optical or cameras. And so once you solve cameras or vision, then autonomy is solved. If you don't solve vision, it's not solved. So that's why our focus is so heavily on having a vision neural net that's very effective for road conditions.
Right, many other people are going the LiDAR route. You want cameras plus radar is most of it.
You can absolutely be superhuman with just cameras. Like you could probably do 10 times better than humans with just cameras.
So
new cars being sold right now have about eight cameras.
Okay, so here's the takeaway. We saw kind of Elon Musk in that video, right? And Elon is talking about the importance of vision, right? He basically says if you solve vision, you solve self-driving. If you don't solve vision, you don't solve self-driving. So vision is extremely, extremely important to solve. Now, where I personally disagree with Elon is on the use of camera alone. And my argument is that we may not solve vision in the same way that humans see it, like the child and the ball falling. We may not be able to get to that. So we may actually have to use sensory information that humans don't have, like using a LiDAR to compensate for the fact that machine intelligence is not as good as human intelligence, right? So give the machine a better sensor, overall making a safer outcome. And I think Tesla is going to start seeing some issues in regulation in terms of its approach to use cameras alone. But that's something that that we can kind of, it's open to some debate. Okay, cool. I want to continue on the slides. Give me a quick moment. With the different areas of computer vision, we won't get through the areas in detail, but I would like you to be aware of the different subtopics you can work on should you decide to specialize in computer vision. So, okay. So this is the organization of computer vision as a field. There's a mountain. Think of this like Mount Everest. At the top of the mountain, there is the goal that we have, right? Teaching machines how to see is the goal of the top of Mount Everest. Now, there are 3 key milestones to that goal. The first goal is representation. We need to be able to represent images in some way so that we can do tasks in vision. And so what this often boils down to is you have an unstructured form of images, like that, and you convert it to a representation that has a measure of what's called invariance. This new representation is an encoding of a complex unstructured image where different images have patterns. Like, for example, cats and dogs have a different representation. And fundamentally what this boils down to is edges and corners and filters. Not so much unlike Hubert and Weasel, right? So the representations we use in AI today are the same representations that triggered that cat neuron. So that's the first kind of 1/3 area of computer vision. The second area is reconstruction. Okay. Given the visual world around us, the word that was used by one of the students in the beginning of the class was you have a visual world. So given that there's a visual world around us, one goal is to reconstruct the visual world. In some ways, that's what self-driving cars are doing. They are trying to reconstruct the 3D map of kind of the world around us, the visual world around us, and navigate a safe path for an agent, like a drone or a car, to navigate on. Why is reconstruction of the visual world so important? Sometimes students come to me and they say, you know what, computer vision is just about pixels. Maybe it's not that important as general AI. And kind of my response there of why computer vision occupies 70% of our brain. Why it's, mapped to so many industry applications is because computer vision is not about pixels. Pixels are just a mechanical representation for capturing spatial information. Computer vision is about capturing space, and if you do it on videos, you're capturing time as well. So if you're capturing space and time, what is space and time? Space and time is everything we know, right? As humans, it's our universe. Our universe is space and time. So in some ways, computer vision is teaching you how to take the information in space-time and process it in some way. And so that's what makes it very, very special. So reconstruction is reconstruction of at least the space part in particular, or also the time, because you have an autonomous car moving at different times. If you have dynamic agents like pedestrians moving in the scene, you need to be able to reconstruct them. So topics here include 3D stereo matching, epipolar geometry, and so on. There's a third R here, which is called recognition. How do you then recognize an image? Recognize a cat from a dog, a safe, area of road to drive on versus a pedestrian. And here is where we look at machine learning methods. Okay. So we look at, for example, CNNs, ResNets, and so on. So you should kind of look at, in this particular case, if you're not familiar, you should look at the progression from AlexNet to VGG, Inception, ResNet. It's good to kind of look at the timeline of these kind of 4 networks. Okay. And with that together, if you have kind of a good skill set in each kind of area, you're hopefully along your way of teaching machines how to see. So we're going to kind of end the lecture there.